Hi, for this video, we will be discussing the integration of trigonometric functions. So in the integration of trigonometric functions, we have to memorize some formulas. We have two sets of formulas. We have fundamental formulas and derived formulas. So the fundamental formulas are the formulas derived from the derivative. Okay, so we have the derivative of sine of u is cosine of u. Okay, so therefore the integral of cosine of u is sine of u. So those fundamental formulas are derived directly from the derivatives of the trigonometric functions, and all you need to do is memorize them, those formulas. So those fundamental formulas again are derived from the derivatives. Okay, so please memorize all those formulas. We also have the derived formulas. Okay, so these formulas are not fundamental formulas because they don't have the equivalent derivatives. Okay, so just unlike in the fundamental formula, so it's derived from the derivatives. The derived formulas for the integrals of trigonometric functions are most using logarithms. Okay, so the integral of tangent of u du is equal to sine of u du over cosine of u. So we have, this can be logarithm where our u is cosine of u and the complete differential of the denominator is negative sine u du. So that's why we put negative here and then negative here. So therefore it will become negative ln of cosine of u plus c. And it can also be equal to ln of secant of u plus c. So why is that? Because we have applied the laws of logarithm. So ln of cosine of u can also be equal to ln of cosine of u raised to negative 1. And cosine of u raised to negative 1, that is ln of 1 over cosine of u, for which 1 over cosine of u is equal to secant of u. Okay, so no need to derive them, so all you need to do is memorize them. So the integral of tangent of u du is equal to ln of secant of u plus c. So another thing, we have the integral of secant of u du. So its formula is derived by multiplying the numerator and the denominator by secant of u plus tangent of u over secant of u plus tangent of u. Okay, so distributing this in the numerator, so this will become integral of secant squared u minus secant of u tangent of u du all over the denominator secant of u plus tangent of u. Okay, so we can also use integrals here, or integrands that lead to logarithms, where our denominator, okay, is secant of u tangent of u, and then its derivative is, derivative of secant of u is secant of u tangent of u, and then the derivative of tangent of u is secant squared u. So therefore the numerator is the complete differential of the denominator. Therefore we can apply the formula for the natural logarithm. So integral of secant of u du is equal to ln of secant of u plus tangent of u plus c. Okay, so similarly with what we did here in the cosecant of u, integral of cosecant of u du, so we multiplied it by cosecant of u plus cotangent of u all over cosecant of u plus cotangent of u. Okay, so the resulting integrand will be this, and the denominator is cosecant of u plus cotangent of u, so its derivative is, so the derivative of cosecant of u is negative cosecant u cotangent u, and the derivative of cotangent of u is negative cosecant squared u. So as we can see, we have a missing negative for both two terms. So we can multiply it outside by negative 1, and then outside the integral sign, we will also multiply it by negative 1. So therefore, it will now become negative ln of cosecant of u plus cotangent of u plus c. So you have to memorize all these 9 formulas. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so no need to derive the this, okay, in the derived formulas. So you can apply this directly. Okay, so if you memorize it, so if you forgot how to, if you forgot the formula, then you can always derive it, okay, to make sure. Okay, so that's it. So let's apply those formulas in some examples. So we have here example. So the integral of cosecant 5t cotangent 5t dt. Okay, so looking at the fundamental formulas, so we can use this one. The integral of cosecant of u cotangent of u du is equal to negative cosecant of u plus c. Okay, so in this case, our u is equal to 5t. So this is still similar with the natural logarithm and the general power formula, where the differential part should be the complete differential of u. So our u here is equal to 5t. Okay, so this. So our differential du should be equal to 5 dt. Okay, so therefore, this must be, so the differential part is only dt, therefore we must add a coefficient of 5. Okay, but writing 5 there as the coefficient of dt, we will also multiply its reciprocal outside the integral sign. So this will become integral of cosecant of 5t cotangent of 5t and multiply it by 5 dt. Okay, so again from the formula, so the du must be the complete differential of u. So we have missing of 5 there, so therefore we need to write its reciprocal outside the integral sign. Okay, so since the differential differential part is now complete, therefore we can now apply the formula. So what's the integral of cosecant of u cotangent of u du? That is negative cosecant of u plus c. So this will become 1/5 times negative cosecant of u, which is equal to 5t. Okay, plus c, or it's negative 1/5 cosecant of 5t plus c. Okay, okay, so next we have integral of tangent theta minus 1 squared d theta. Okay, so for this problem, we can first expand this binomial. So expanding that, it will become tangent squared theta minus, so 2 times tangent theta times 1, so that will become 2 tangent theta plus 1, okay, d theta. So let's inspect the terms if we can integrate it. Tangent squared theta, we don't have an integral of tangent squared from the formula, right? So therefore we can't integrate that. 2 tangent theta, we have the integral of tangent theta. It's under the derived formulas. Okay, so it's equal to ln of secant. and integral of 1 d theta, so that is theta. Okay, so our problem here is the tangent squared theta. Okay, so but if we recall our identities, so we have there 1 plus tangent squared theta is equal to secant squared theta, right? So therefore, this will now be equal to tangent squared theta plus 1. We can replace that with secant squared theta. So it will now become integral of secant squared theta minus 2 tangent of theta d theta. Okay, so applying the properties of logarithm, so integrating each term, so it will become integral of secant squared theta d theta minus, we have a numerical coefficient, so we can write that outside the integral sign, so minus 2 integral of tangent theta d theta. Okay, so we have theta only, so therefore its complete differential is d theta. We have our u here as theta, then its complete differential is d theta, so we don't need to add any coefficients. Okay, so let's recall the formulas. Integral of secant squared u du is equal to tangent of u plus c. And for the second term, integral of tangent is ln secant. So therefore, we will have integral of secant squared theta d theta is tangent of theta minus 2 integral of tangent squared theta, integral of tangent theta is ln secant. Okay, plus c. Okay, so for our last example, so we have integral of sine cube y dy over 1 plus cosine of y. Okay, so in this problem, so what we actually need to do here is to transform, okay, the equation or the integrand. So we have here sine cube y dy, okay, and then we have here 1 plus cosine y. So here we will apply the identities, okay, so especially for sine and cosine. So we know that from the identities we have sine squared theta plus cosine squared theta is equal to 1. Okay, and that transposing cosine squared on the other side, so we will have sine squared theta is equal to 1 minus cosine squared theta. Okay, so we can separate sine squared from sine cube, so we'll have integral of sine squared y times sine y dy over 1 plus cosine of y. So this is still sine cube y, right? So but we will replace sine squared y with 1 minus cosine squared y. So it will become integral of 1 minus cosine squared y times sine y dy over 1 plus cosine of y. Okay, so but we know that 1 minus cosine squared y is a difference of two squares, so therefore we can factor that out. We will have integral of, so 1 minus cosine squared y, so that is equal to 1 plus cosine y times 1 minus cosine y times sine y dy. over 1 plus cosine of y. Okay, so as you can see, we can cancel out 1 plus cosine of y because it's a common factor in the numerator and the denominator, and then we can distribute sine y in one and cosine y. You can also distribute the integral sign, so this will become integral of 1 times sine y dy. So integral of sine y dy minus integral of cosine y times sine y dy. So we will have integral of sine y cosine y dy. Okay, so how do we integrate this? Okay, so integral of sine y dy. So from the formula, so we have the integral of sine, which is equal to negative cosine. So how about integral of sine y cosine y dy? Okay, so we have two methods. Okay, first one is we can apply the power formula, wherein we select one as our u and then the other one as our du. Okay, so we can select sine y as our u and then du is cosine y dy, or we can select cosine y as our u and then sine y dy as our du. We can also use the double angle identity for sine. Okay, so sine 2y is equal to 2 sine y cosine y dy. So we have actually three solutions, okay, for the second integrand, I mean. So let us solve each one by one maybe. So the first one is we have integral of sine y dy minus integral of, so we can select 1 as our u. So this is our first solution. Okay, so we can let u is equal to sine y so that we can apply the power formula. Sine of y raised to 1 and then cosine y dy. Okay, so to apply the power formula, our u here would be sine y. Okay, our n is equal to 1. So our complete differential, so du should be, so differential of sine y is cosine y dy. So the differential part is already complete, then no need for us to multiply any coefficient. Okay, so therefore we can now apply directly the power formula. So the integral of sine y dy is negative cosine of u. Okay, so we have here y, dy is the complete differential of y, so therefore we don't also need to multiply it by any coefficient. So the integral of sine y dy is negative cosine of y minus, so we can apply here the power formula. So we have u raised to n plus 1 over n plus 1. So we will have sine y raised to 1 plus 1 over 1 plus 1 plus c. So this will now become negative cosine of y minus we have 1/2 sine squared of y, okay, plus c. Okay, so that is for our first solution. So for our second solution, we will let u as cosine y. Okay, so we will have equal to integral of sine y, so copying from here, sine y dy. So if we let cosine of y as our u, so cosine of y raised to 1 and then sine y dy. Okay, So then if our u is equal to cosine of y, then our du must be differential of cosine is negative sine y dy. Okay, so we have a missing negative here. So therefore, we should complete the differential part. So this will become sine y dy minus integral of cosine of y raised to 1 times sine y dy. So again, we have a missing negative sign to complete the differential. Then we must also write negative outside the integral sign. So we can now integrate this. So sine y, integral of sine y dy, so nothing has changed. So it's still negative cosine of y. Okay, so in this, for the second term, so negative, so plus power formula. So we have u raised to n plus 1. So you have cosine of y raised to 1 plus 1 over 1 plus 1 plus c. Or this is equal to negative cosine of y plus 1/2 cosine squared of y plus c. Okay, so this is our second answer. So our first answer and then our second answer. Okay, so for the third one, so we can use the identity, double angle identity. So we have equal to, so copying again this one, so integral of sine y dy minus integral of sine y cosine y dy. Okay, so using the double angle identity, for sine, so we have sine 2y is equal to 2 sine y cosine of y. Okay, so dividing both sides by 2, so therefore sine y cosine y is equal to 1/2 sine of 2y. So we can replace this with 1/2 sine 2y. So this will become integral of sine y dy minus integral of 1/2 sine 2y dy. Okay, so we can write 1/2 outside the integral sign. So you have integral of sine y dy minus 1/2 integral of sine 2y dy. Okay, so we have the integral for sine. Okay, however, the differential part here, the dy, should be the complete differential of u. Okay, so we have here 2y, its complete differential should be 2 dy. So therefore, we must multiply here by 2, and then here multiply by the reciprocal of 2. So this will become integral of sine y dy minus 1/2, provide space, sine 2y, complete differential of 2y should be 2 dy. Okay, so since we multiply 2 here, so we must multiply again outside the integral sign by 1/2. Okay, so this will become integral of sine y dy, so nothing has changed, it's negative cosine y. However, here, so we'll have, minus 1/2 times 1/2, that is 1/4. Integral of sine 2y is negative cosine of 2y plus c. So simplifying the answer, we will have negative cosine of y plus 1/4 cosine of 2y plus c. Okay, so we have 3 sets of answers for the third problem. Okay, so basically, to sum it up, so for the integrals of trigonometric functions, so you, aside from memorizing the fundamental and the derived formulas for integration, okay, you also have to recall the trigonometric identities. Okay, so the different trigonometric identities from your trigonometry. So as you can see, it's very useful. Okay, in problem number 2, here problem number 3. Okay, so we have used different identities. Okay, so that's it for this video, and good luck.